This is section 11.5, Circumference and Areas of Circles. Consider these inscribed polygons. Polygons inscribed inside of a circle. I've got a square, hexagon, an octagon, and a decagon. As we increase the number of sides of the inscribed polygon, we fill up more of the circle. And the polygon itself becomes a better and better approximation of the circle. As I have more and more sides, there's less and less space between the polygon and the circle. There's a lot of space with the square, not much space at all with the decagon, but there is space. And if I increase the number of sides, there's less and less space. Now, even if I had 1,000,000 sides, it still would not be an exact circle, but it would be very close. And making approximations like this allows us to approximate the area of a circle and to think about what the area of a circle means in relation to an inscribed polygon. And notice the perimeter of the inscribed polygon also gets closer and closer to the distance around the circle, the perimeter of the circle in a way. If we look at this chart, we'll see exactly that happening. As we increase the number of sides in the left-hand column, the perimeter and the area are both increasing, but notice they're increasing to almost the same value. As I jump from 30 sides to 100 sides, there's not much jump at all in the perimeters or in the areas. That's a big jump in the number of sides, and it's not leading to much of a difference in the perimeter and the area. What that means is that as the number of sides increases, the area of the inscribed polygon approaches the value of the area of the circle. And it also approaches a limiting value, a value it's not going to go over, even if I keep adding more sides. And we define that limiting value to be the area of the circle. Notice the actual value it's approaching. So r here is the radius. So if the radius is r, and we square that, and we multiply that by 3.14, then we're pretty darn close to the area of the circle. 3.14 should ring a bell because it's an approximation of the mathematical number pi, which is more than just 3.14, but you'll see we're getting closer and closer to pi times r squared for the area. And the perimeter, 6.28, is just double 3.14. So the perimeter is getting closer and closer to 2 times pi times r. As the number of sides increases, the perimeter of the inscribed polygon approaches a limiting number, which we define to be the perimeter. So that number, that value, that the perimeters of the inscribed polygons are approaching as we increase the number of sides, is defined to be the perimeter of the circle, which we have a special name for. We call it the circumference of the circle. So the circumference of the circle is essentially the perimeter of the circle. It's the measure around the circle, whereas the area is measuring the inside of the circle, how much space the circle is filling. So the area A of a circle equals pi times r squared as our chart is approaching that. So that's the way we define it. This number pi times r squared, where pi is that limiting value that the areas of the inscribed polygons are approaching. And the circumference c of a circle, the distance around the circle, is defined to be 2 times pi times r, the radius. Take the radius, multiply it by pi, and then double that, which is what our chart is approaching as we increase the number of sides. We have 6.28, which is 2 times 3.14. So those are our formulas. Let's just summarize that down here. The circumference is 2 times pi times r, but if you take the radius and you double it, what do you get? You get the diameter. So the circumference could also be defined as just pi times the diameter, because 2 times the radius is the diameter. The area is pi r squared. Pi times the radius squared. We define pi to be the ratio of the circumference of a circle to the diameter. The ratio of the circumference of a circle to the diameter, which would make sense if the circumference is pi times the diameter. We take the ratio of that to the diameter, and we're dividing by the diameter on both sides, and that just gives us pi. So we define pi to be that ratio. The relationship, in a way, between the diameter of a circle and the distance all the way around the circle. Pi is a number. It's an actual number, but it's an irrational number. Irrational because it's not rational. Rational numbers are the numbers that can be written as fractions. Pi cannot be written as a fraction. There is no fraction that expresses pi exactly, and there is no finite decimal that expresses pi exactly. We can only get closer and closer to pi. And in fact, mathematicians are still trying to get a better and better approximation of pi. This is a website called piday.org/million, and it gives the first 1 million digits of pi. If I can get it to stay up here. So as you scroll down, notice it's 3.14, 1592653589793238462, and so on. And they've got 1 million digits. And I scrolled through this earlier for almost five straight minutes and never got to the bottom. It'll keep loading more and more digits as you go down. So the way they come up with that approximation, or one way to do it, is to do what we were doing before and take inscribed polygons and find the areas of those. They find the areas of those using some trigonometry. And then they just keep increasing the number of sides on the polygon to get a better and better approximation. Here's some examples of how to use circumference and area. Find the circumference and area of a circle with a radius of 6 centimeters. So the circumference equals 2 times pi times the radius. So here that's 2 times pi times 6, which is 12 pi. We're going to leave pi in our answers. We're not going to go to a decimal. We're not going to go to our calculator. We're going to leave pi in there because that is an exact value. If I put in 3.14 for pi, I'm getting only an estimate of an answer. I'm not getting an exact answer. So I'm going to leave pi there. I'm going to put units on my answer, and it's 12 pi centimeters. The area is pi times the radius squared, which is pi times 6 squared, which is pi times 36, and we usually write the number in front of pi, 36 pi. And the area is always going to be in square units, centimeters squared. 36 pi centimeters squared, square centimeters. Number 2, find the circumference of a circle if the area is 25 pi square feet. So the area is 25 pi. But we know the formula for area is pi r squared. So we're going to take this equation. We're going to solve it for r. We can divide both sides by pi. And we'll have 25 equals r squared. If we take the square root of both sides, we'll have that r equals 5. And then we can find the circumference by plugging that into the formula, 2 pi r. 2 times pi times 5, which is 10 pi. And we've got to put feet on our answer because our units were in square feet. The circumference will just be regular feet, not square feet. The area will be squared. Okay, you're going to do exactly that process on your immediate practice problems. Number 1, find the circumference and area of a circle with a radius of 15 inches. It's just like example number 1. Number 2, find the circumference of a circle if the area is 81 pi square yards, just like example number 2. And that is the end of section 11.5.